Centripetal force is the net force acting toward the center of a circular path that keeps an object moving in uniform circular motion. It is not a new type of force, but a role played by forces like tension, gravity, or friction. Without centripetal force, an object would travel in a straight line, according to Newton's first law. Newton's second law governs centripetal force. The net force equals mass times centripetal acceleration, which is always directed toward the circle's center. This acceleration arises from continuous direction change, even at constant speed. Two equivalent expressions for centripetal acceleration are v squared over r or omega squared times r. Here, v is linear speed, r is the circle's radius, and omega is angular velocity in radians per second. Thus, the net force equals m times v squared over r, or m times omega squared times r. Direction is crucial. The net force component toward the center must equal mv squared over r. For a car turning on a flat road, static friction between tires and road provides centripetal force. The maximum speed before skidding is the square root of mu s times g times r, where mu s is the static friction coefficient. On a bank curve, a car navigates a curved incline without friction. The horizontal component of the normal force supplies centripetal force. Tangent theta equals v squared over rg, where theta is the banking angle. For vertical circles like a ball on a string, at the circle's bottom, tension force opposes gravity, so tension minus mg equals mv squared over r. At the top, both tension and gravity point downward, so tension plus mg equals mv squared over r. The minimum speed at the top for circular motion is the square root of rg, when tension equals 0. For planetary orbits, gravity acts as centripetal force. G times mm over r squared equals mv squared over r. Problem-solving strategy includes: draw a free body diagram labeling all forces, identify the center of the circular path, sum force components toward the center and set equal to mv squared over r or m omega squared r. Resolve forces in radial directions, such as horizontal or vertical for bank curves. Avoid centrifugal force misconceptions. This outward force is fictitious and only appears in rotating, non-inertial reference frames. In inertial frames, centripetal force is the only real radial force. For example, a car rounds a 50-meter banked curve at 20 meters per second. Calculate the ideal banking angle with no friction. Solution: tangent theta equals v squared over rg, which is 20 squared over 50 times 9. 8, approximately 0. 816, so theta is approximately 39.2 degrees. This video is part of our free physics course for students, covering centripetal forces and more. We're excited to share the full course with over 100 lessons. Find the link in the description.